So, welcome to lesson 8 of the electricity unit of work, and this lesson is on series and parallel circuits. So as you'll see on your current page, you've got some information from the specification detailing some of the key points we're going to try and learn today. And if you have a look onto your next page, you'll find a knowledge check just summarising some of our key content from previous lessons in this unit. So can you pause the video there and can you start to have a go at this knowledge check for me, please, on your printout or just in your own notebook, trying to answer these questions. Right, you should have unpaused the video, so let's just reveal the answers for you nice and quickly. So you've got a symbol for a thermistor, symbol for a diode, symbol for a lamp, one for a resistor, a non-ohmic conductor would be a lamp, a diode, an LDR or a thermistor where the relationship between current and voltage is not directly proportional. Describe how the resistance of a thermistor changes with temperature. Decreases as temperature increases. You can also have the opposite. Describe how the resistance of an LDR changes with light intensity. The resistance increases as light intensity decreases. Just remember as well with both of these, you could also have put the opposite, and that would still be absolutely true. Resistance increases as light intensity decreases, etc. And then maybe use for an LDR, lighting circuits in streetlights and also automatic light bulbs. Right, so we're going to look at the resistance of resistors in series circuits and then the current and potential difference in the resistance in direct current circuits as well. So let's have a look at this little paragraph at the bottom, which, if we just read it through together, when resistors are added in series, so as you remember in series where there's just one single pathway for current to flow around, the current in each resistor is the same. So remember, we might have represented this before as, for example, A1 equals A2 equals A3 in circuit diagrams. But the potential difference is shared between the resistors. Since the potential difference is shared, now, we might have seen this represented, such as total voltage equals V1 plus V2 plus V3, different voltmeters in the circuit, worth remembering that. As more resistors are added, it's harder for the current to pass through as more resistors are added. In other words, adding more resistors increases the resistance. Important relationship there to remember. Adding more resistance increases the resistance. So, if you think about it, the total resistance of a circuit, like this one here, is the sum of both of the resistors in it. So if you add more resistors, you're going to have a higher resistance, which means it's going to be harder for the electrons flowing around the circuit to move through it, which means the current is going to be lower. So you might make your own annotations there, just your own notes, nice and quickly. And then if we have a little look now just quickly at the checkpoint question on your next page, just pause your video for a moment and see if you can answer it. If two resistors are connected in series, what can be said about the total resistance? Pause the video, try and answer that, and then we'll just reveal the answer. So, unpause the video, and you'll see the answer is that total combined resistance is equal to the sum of the individual of the two resistances. So in a nutshell, R total equals R1 plus R2, etc. if you've got more resistors in the circuit. Now, what about resistors in parallel? So, in contrast, when resistors are in parallel, so if you remember resistors being in parallel, that means they've got two or more pathways for the current to flow down. The potential difference is the same. You might see that represented as V1 equals V2, etc., etc., across the resistor, but the current is split. So the current might be the same at the start and the same at the end, but then it's split across the different branches, the different pathways. This means adding more resistors makes it easier to push the current through as there are more pathways for it to flow down, but each has the same voltage pushing the current through it. So the total resistance of two resistors is less than the resistance of the smallest individual resistor. Now that can be confusing. So in a nutshell, in a parallel circuit, if you add more resistors, the total resistance of the circuit gets smaller, reduces. And that's what this checkpoint question is about. If two resistors connect in parallel, what can be said about their total resistance? The total resistance is less than the smallest of the two individual resistances. So if you were to look at this circuit here, so what we're saying is that for our parallel circuit, the voltage of these two is the same. The current here and here is the same, but at A2 and A3, instead of the current being the same, what happens is some of it flows down there, and some of it flows down there, which means there are more pathways. There are more pathways, and if there are more pathways, it's easier for the current to flow, which means you've got lower total resistance. It's important to bear in mind that the total resistance of the circuit is usually less than the resistances of the resistors on the individual pathways. Right, now have a little look at this question here. A student wants to demonstrate the difference between equivalent resistances of two resistors in series and parallel circuits. Describe how they should set up two circuits, one in series, one in parallel, and show the difference. You need to draw a circuit diagram for each. Describe the measurements the student should make and how the student should use those measurements to calculate the equivalent resistance of each circuit. Describe the differences in the equivalent resistance that you should find. So we've done part of the answer here if we were to model it. If we go back and to look at this circuit, we've got two resistors in parallel because we've got two different pathways. So that would be how we'd set up our parallel circuit. Whereas our series circuit, we've got two resistors in the same pathway. So the current can only flow down the one pathway. Now, two examples. So, if we have a look at the mark scheme, we've got those two circuits drawn. Great. Where it says bulb, I think it should say resistors in these. I think there's a typo. No, it should say resistor. So you need to measure the total current in each circuit and the potential difference of the supply. So if you're measuring the potential difference of the supply, you're going to have the voltmeter over the battery. So you need a voltmeter over this battery as well. Okay, now, what equation do we know that links voltage, current, and resistance? That's right, V equals IR. Voltage equals resistance times current, which if we rearrange, resistance equals voltage divided by current. So this is the equation that we'd then want to use, taking measurements from both circuits. And then rearrange it, and then we'd use it to calculate the resistances. And what would we expect? We would expect the resistance on the series circuit to be bigger and the resistance on the parallel circuit to be smaller. So you might want to re-watch that bit of the clip, and if you want to make any notes on that answer, that's absolutely fine. But that's just how you might tackle a really difficult question on looking at relationship current and resistance. Now I say relationship, the relationship between current, resistance, and voltage. That's what I meant. Right, we had a go at that. Hopefully you've made quite a few notes. So what I'd like to have going now is I'd like to have a go at some series and parallel circuit diagrams using some of the different components that we've spoken about in previous lessons. So you're going to need to draw some circuit diagrams involving some different components: lamps, batteries, resistors, diodes, variable resistors, and in parallel or in series. So how much of these can you do from memory? Pause the video now and have a go at them. When you think you've done as many of them as you can, either in series or parallel, unpause the video, and then we'll just show you a couple of the answers. Right, hopefully you've had a go and you've done what you can. Unpause the video and let's see the answers. So your 2 lamps in series, 1 pathway. Your battery and 2 lamps in parallel, so you've got 2 pathways. Just make sure you've got those recorded. Correct your work if you didn't quite get those. Change them if needs be. Give yourself a mark if you did. Circuit containing a battery, a resistor and diode. So 3 different components. You've got a battery, you've got a resistor, and you've got diode. In series in 1 pathway. A circuit containing a battery, a variable resistor in series with 2 lamps in parallel. So as you see, the lamps in parallel, they've got 2 possible pathways down which they could go, whereas the variable resistor is just in 1. Then circuit to measure the current series in 2 resistors. Had a look at this already. That's how we do it. And then draw a circuit which could be used to measure the resistance of a component. So this would be the resistance of the component that you're measuring. This would be, when you're measuring, you'd need your voltage, you would need your ammeter, and you'd need your variable resistor, because your variable resistor would change the resistance. It would give you a voltage and it would give you a current. So you take these 2 readings, and resistance equals voltage divided by current. Good, so correct any of your work there you didn't quite get right. If needs be, just skip back and have another look at it. And once you've done that, carry on onto the next page. So, on the next page, need to put some more into practice now. So, a couple of different key questions here. Calculate the total resistance of 2 resistors in a circuit. So what have we learned already? R total, if you look back in your notes, you'll see equals R1 plus R2, etc. Have a look at the second question. Calculate the reading on the voltmeter. Ohm's law. Remember, Ohm's law is V equals I R. And it says replacing one of these resistors with a resistor of a higher value will decrease, not change, or increase the reading on the ammeter. Pause the video and have a go at these questions now. Once you've done that, unpause and I'll walk through the answers with you. Right, so have you had a go? Total resistance, R1 and R2. So on our circuit here, we might have R1, R2, add them together, you should end up with 15 ohms. Give yourself a mark if you got it right. Calculate the reading on the voltmeter. V equals IR. So, do we have an I for this? Yes, we do. 0.3. 0.3. Do we have a resistance? Well, we've got 2 resistances. We've got 9. We've got 6, which we know gives us the total resistance of the circuit. Gives us 15. So we should have 0.3 times 15, 4.5 volts. As you'll see, correct answer. So, replacing one of the resistance with a resistor of a higher value. So resistance of a higher value is going to increase the resistance, isn't it? And if you've got a higher resistance, does that mean your current, which is measured by the ammeter, the flow of the electrons, is it going to make it easier or harder for it to move around? Now it's going to make it harder, so what's that going to do to the reading? It's going to go down because there's going to be a lower flow of current. Good. Right, have a go at that. Correct anything that you've got incorrect. Just make sure you've got those notes there if you need them. Have a look at the next questions. Parallel problems. Complete the following sentences using the following: greater than, lesser than, or same as. So, pause the video. See if you can work out what would go in the gaps from greater than, less than, or the same as. Right, unpause the video And as you'll see, the current through the ammeter is greater than the current through the resistor. The potential difference across the battery is the same as the potential difference across the resistor. The current through the lamp is less than the current through the battery. And the potential difference across the lamp is the same as the potential difference across the resistor. Good, right. So, now, pause the video and move on to the questions on the next 2 pages for me. So, using various bits of information, such as Ohm's law and other such, rearranging them, can you have a go at the following questions for me, please? Okay? Have a go at those questions, see how many you can do, and then we'll go through the answers. So pause the video now and have a go at these independently, please. Right, so unpause the video. You should have some answers, so mark them, correct them as we go through them, please. Show that the current through the resistor is 0.4 amps. Use Ohm's law. So, Ohm's law, as we know, V equals IR, voltage equals current times resistance. So we need to know I. So I equals V divided by R. So that gives us, we know that the answer to that is 0.4 amps. So in figure 1, the cell has a potential difference of 2 volts and the resistor has a resistance of 5 ohms. Oh, we've got a V and we've got an R. What do we do with those 2 numbers? We divide them. So we have 2 divided by 5. And as you'll see in our answers, 2 divided by 5 is 0.4 amps. Now the ammeter reading is 0.9 amps. Calculate the current through the lamp. So in our current, if in our circuit, up here, the total current, because it's at the end. So the total equals 0.9 amps, doesn't it? Now, calculate the current through the lamp. Lamp, resistor. So the resistor is going to have an impact. Right, so calculate the current through the lamp. Total is 0.9. So if we think about what the current through the resistor and the lamp is. So total current is 0.9 amps, which is the current through the resistor and the lamp, isn't it? Good. So what's current through the lamp? Just the lamp. It's going to be 0.9. So what is our current in our resistor that we need to take away from our 0.9? Any ideas? Well, you'll find it. Oh, not down there. Apologies. You'll find it there. It's 0.4 taken away from 0.9 gives you 0.5 amps. And there's your answer. Calculate the resistance of the lamp in this circuit. So R equals V divided by I. So what is RV? Well, we should see. It's 2. What is RI in the lamp? We should see. It's 0.5. Divide them. 2 divided by 0.5 is going to give you 4. And if it's resistance, it's ohms. And you'll see, there's your answer. Good. Right. On to the next questions. So hopefully you've had a go at these 2. So calculate the current through the 10 ohms resistor. Use Ohm's law. So remember, calculate the current, which is I. So I equals what? I equals V divided by R. Because remember, Ohm's law is V equals IR, so it's rearranged. So what is our voltage? It gives us it right here, 12. What is our resistance? Gives it us, we've got 10 ohms resistor. 12 divided by 10 give us 1.2. Because it's current, it should have amps. And as you'll see, correct answer again. Calculate the current through a 15 ohm resistor. So, same idea. I equals V divided by R. What is our V? 12 stays the same. What is our R? In this case, it's 15 now. Divide it, should be 0.8 amps. Calculate the current through the battery. It should be the same as the total current through the resistors. Total current. So what's the total current? We've got current through 10 ohm resistor and the current through 15 ohm resistor. 1.2, 0.8. Should be the same as the total current through the resistors. So what do we need to do with those two numbers? We add them. 0.8 plus 1.2 equals 2 amps. What would be the resistance of a single resistor that would have the same current if it was connected on its own in the same battery? So we want to know what would be the resistance. So resistance equals V divided by I. Would have the same current if it was connected on its own to the same battery. So we need to know the voltage of the battery. And it's the same for everything. So the voltage from the battery back up here, 12. So we know that that's 12. Now, what would be the resistance of a single resistor that would have the same current if it was connected to its own on the same battery? So a single resistor that has the same current as the two in the previous questions, which is 2 amps. So it becomes 12 divided by 2 equals 6 ohms. Good. So make sure you've got those down. Pause the video, go back if there's anything you're not sure on. Make sure you corrected any of your answers that you didn't get right. And then to go on to the next page, can you now have a look at just the knowledge check questions, which are purely true or false. Pause the video and see how many of them you can get. Right, hopefully you've had a go at them. And just put true or false to see whether the answer is it's true or false, whether it's right or wrong. So 1, true, 2, true, 3, true, 4, false, false. False for a series circuit, true, not true for a parallel. True, true, and then remember your magnetism, false and true. So just quick true or false, correct any that you've not quite got right. And then to finish, have a look for me please now at these sets of knowledge recall questions. Pause the video and just have a go and challenge yourself. How many of these can you do on a notes page from memory or just using the notes that you've made over the past few lessons? What can you do? What do you understand? What do you need to come back to? So pause the video, have a go at them now. Right, if you want to pause the video because you've had a go at these, I'll just give the answers over to you. So the answers are all on the page here in order. So mark them, correct them as you see fit. And then once you have done that, that is the end of this lesson. So if needs be, just make sure you have a look at the summary videos at the end or the extension videos just to